Okay, so let's take a look at computer organization. Now, this is basically a lecture on some of the internal workings of how the code you guys write is actually being used in terms of the hardware, okay? But it's not an electronics lecture. I'm not here to be an electronics teacher with you guys. So let's first of all take a look at what the IB actually says about this. Okay, come on, why is this not working? There we go. Okay, so here's the points the IB wants you to know. Outline the architecture of the CPU, Central Processing Unit, and the functions of the ALU, the Arithmetic Logic Unit, and the Control Unit, the CU, and the registers within the CPU. So this will be new to you, so that's what I'm going to teach you. Explain the machine instruction cycle, the main functions of an operating system, and the range of application software. We're not going to do all these points today, but let's dive into this, okay? All right, so here's the visualization. On this wall over here, imagine it is filled with tiny light bulbs. Okay, you guys visualize that? So on this wall, imagine it was entirely covered with tiny light bulbs. Now, imagine this far wall is entirely covered with light switches, like these switches here. Okay? Every switch on this wall connects to every light bulb on that wall. Now, imagine this wall also contains switches, but a lot less switches. Not as many as this wall. It also contains switches. And it just so happens that if I flick a switch here, it switches a sequence of switches here to make the letter W appear on that wall. Does that sound like something that those of you guys taking electronics could do? Seems pretty simple, right? That's what a computer basically is, okay? This wall is essentially your keyboard sending a command to this wall, which then figures out which switches to connect to make that wall appear. Now, forget switches and lights. Let's call those things ones and zeros, okay? Let's call this wall your code, and let's call this wall your user. So your user interacts with your code to make ones and zeros appear. The ones and zeros aren't real either. Ones and zeros are just what we say. In reality, it's basically just on-off, or positive-negative, or true-false, okay? So basically a computer is just a collection of switches, okay? It needs a way to switch something on and off, okay? And the way it does this is through microscopic transistors and a special material called silicon that helps do this, okay? Now, again, the master switches are just the logic and the code that we write and the hardware that implements the code to turn the switches on and off, okay? So at its core, the computer is a simple device. It's just a set of switches. Now, in the early days of computers, those switches were mechanical, just like this switch, right? Like this is mechanical. It's a very mechanical looking thing. They often used magnetics to actually switch them. Okay? Later, those switches became more electrical, but they were much larger and they heated up and they were hot. So if you guys have ever seen like pictures on like history shows of old computers, there were these giant things that took up rooms worth of space because they didn't have a way to make those switches smaller. They knew what they had to do. They just needed a way to get it smaller and smaller and smaller. And that's where technology has developed over the last 30 years, is making those switches smaller and faster. Okay? So really, a switch is just an on-off, which we often show as ones and zeros. Okay? Now, if the world is ones and zeros, we can do math with ones and zeros, right? As a matter of fact, it's super easy math with ones and zeros. We can add them, right? 1 plus 1, 0 plus 0, 0 plus 1. That's pretty easy. Adding is the base of all mathematics. Now, you may not believe me when I say that, but it's true. You can use adding to do everything, right? So for example, I'll just use this thing because I just need a blank here. Okay, as I said, I can add those numbers, right? But in reality, there's only two numbers, 0 and 1. We think of math in a different system. We think of math as 0 to infinity, okay? And also negative infinity. But in reality, we use a system of math that you guys have been familiar with that uses 10 digits 10 different digits to create all the numbers between negative infinity and positive infinity. What this is called is the base. We use what's called base 10 math. We use 10 numbers to express this. Computer doesn't. It uses base 2 numbers, which are really just 2 switches, on, off. But it's the same thing. We can still do math. So with only 2 numbers, adding them is easy. Right? Is there any other sequence I've missed? 1 plus 1. That's it. That's the only possible number of sequences that we can deal with here. Right? And these two are essentially the same question, just in a different order. That's it. That's really all there is. And we'll get our answers, right? And luckily, our answers also fit our base. Right? 0, 1, 1. Oh, wait. No, it doesn't. The answer to 1 plus 1 is 2. I can't use 2. I can only use 1 and 0. Well, we do this in regular math as well, right? If I said, what's 5 plus 5? The answer I put here isn't in the bases, right? There is no number here that will go there. So I have to use 2 from my base. I have to use the 0 and the 1 because now I'm moving to the next sort of column here. Well, exactly the same thing happens here. I can put 1s and 0s to create the number 2. And we're going to learn about how that works in this unit, but the core of this is I can add these numbers. But how am I going to subtract the numbers? Well, subtraction is actually a trick, okay? Because 5 minus 2 is equivalent to 5 plus negative 2, right? It's the same thing. So I can just use adding as long as I can create negative numbers. If I can make a number negative, I don't need subtraction. I can just use adding. Now what about multiplication? 5 times 3. How could I express that using just addition? Right, 5 plus 5, right? Repetitive addition. Oh, repeating things. Oh, I know how to do that as a computer. I'm a machine. I'm good at repeating things. As a coder, you know that's looping system. So really, multiplication is just repetitive addition. And believe it or not, division is just repetitive subtraction. Think about it. It's repetitive subtraction. But wait a minute, what's subtraction? It's addition of a negative number. So division is really repetitive addition of a negative number. So our 4 basic math operations really can all be reduced down to 1. That's it. That's all I need. And then from here, we build more complex things like exponents and square roots and logarithms and all that. But they're really all based on those 4 basic math operations. And really, all 4 of those basic ones are just about this. So here's the reality. These fancy things that you guys used to check Facebook on and go on Twitter are really just machines that add things, and they only add 2 numbers. That's it. That's what's in front of you right now. A machine that just does adding of 0s and 1s. That's it. It's just really, really good at it. It's really, really fast at it. And that's why it's so fast. It's so fast because I've given it such a simple job to do that it can do it incredibly fast. Okay? So that's the beauty of the machine itself, is that it is simple at its core. But then we build the complexity on top of that. Okay? So that's what this is saying, that everything on the computer is 1s and 0s and everything is adding. Okay? The first computers used mechanical things like vacuum tubes to generate the 0s and 1s or the on-off switches. Okay? We have evolved it smaller and more efficiently. Okay? We also have evolved something called Boolean logic, which is logical gates, which adds to the whole math thing by allowing things like and, or, and not, and things like coding if statements to occur. Okay? But let's take a look at how this works in the transistor stage. Okay? So this is how it works. Okay? At a microscopic level, we have some compound known as silicon dioxide. Okay? And then there's some stuff, different forms of silicon. There's a polysilicon, and then there's something called N and P-type silicon. Don't worry about that. You don't need to know that. As you saw at the beginning, that was not on the IB curriculum, okay? What you do need to know is that this thing is essentially an on-off switch. You guys probably know from science class that electrons, which can be positive and negative, do they attract each other or repel each other? Repel. Okay? So in other words, if I push a bunch of positive electrons down here, what's it going to do to all these little negative electrons here? It's going to push them away, right? It's going to say, whoa, whoa, get away from me. Get away from me, you positive electron. Okay? In other words, the flow of negatives going this direction, if we think of them flowing from the source through the drain, the second I start pumping positives down here, it shuts off that flow. In other words, it turns this thing off. The second I stop bringing these positive electrons here, those do flow through. In other words, on. And that's essentially how it works, okay? Is it basically changes the electron state of these things at a very, very small level, at that microscopic level, to signal on and off. Now remember, this is incredibly small. But using that silicon material, okay, which is, by the way, why they call it Silicon Valley, right, because it's such an important part of the process, is you can create that on-off switch, okay? This is more than you need to know. I'm just sort of giving you the actual mechanics of what's going on there. Okay, so from there, we developed something called the microprocessor. Now that we can turn things on and off at a very small level, we can create something called the CPU. This you do need to know. CPU stands for Central Processing Unit. Essentially, it's the brain of the computer, okay? All the other components, disk drives, monitors, keyboards, mice, RAM, etc., they basically are helping the microprocessor get everything done. It's the workhorse that does everything, okay? Now, if you actually take a look in that back computer in the corner, okay, it is actually one of these, an 8086 generation microprocessor. It moved up from there to the 286, the 386. Ask your parents. They'll remember something called 486 computers. That was actually the most popular brand back in the 90s of selling computers. We don't call them that anymore. Your parents might also remember something called Pentium computers. Okay? You generally don't hear those words anymore, but essentially it was moving up in generations. They still do, obviously, do that, but we tend not to call them by those names anymore. As a matter of fact, I don't even know. I'm not really into hardware enough to actually know that stuff as much anymore. But let's move down a bit. Inside the CPU, it is actually a little bit more divided. So just jump over here for a sec. Okay? So inside your computer is this big thing called the CPU. What does that stand for again? Very good. But inside there is something called the ALU. Well, what does U mean? Unit. Okay, let's try and figure out what A and L would stand for. Logic. Yeah, L is logic. And A, go back here. What do you think A stands for? Add. Close. It is add, but it actually stands for arithmetic or arithmetic. So it's the arithmetic and logic unit. That's what it stands for. It's not the adding and logic unit, though maybe it should be, right? Because that makes more sense. But that's a unit that does math. This is the math thing. And as we know, the math is actually pretty simple. But that part of the CPU is designed just for adding. Okay? Really, this thing is doing the processing part. Right? It's processing or doing math on it. So which piece is missing? The C, right? And what does C stand for? Central. But there's actually another piece of this called the CU. Okay? But it doesn't actually stand for central here. What it stands for, in this case, is control. This is the control unit. Because this central processing unit is in charge of the whole deal, it needs to be in control. So every CPU contains an ALU to do math and a CU to take control. Okay? Now, it is a little more complicated than that, okay? So for example, they've split the ALU to deal with integer variables and decimal variables, or floating point numbers, right? So that they separate that so that they can each do different types of math. You don't need to know that, though. That's nothing you need to worry about, okay? But the ALU and the CU are the two main components to a central processing unit. Those things are communicated between them using something called a bus. Now, bus is a very general term, and it means the same thing it means in the real world. It's a way to get information or people from one place to another. So buses are essentially wires, right? It's what wires these two things together. So the word bus is very general. You'll hear the word bus in lots of contexts, right? Like there's this bus and there's that bus inside the hardware. But really, bus just means a connection, okay? So for example, there's something called the control bus, and there's something called the address bus, okay? And the CPU sends instructions to the ALU, etc., okay? So let's try and kind of break this down how this works, okay? One, when you load a computer, let's say it's a computer game onto your computer, the first thing it does is it loads it off your permanent storage, like a hard drive, into RAM. Now, what do you guys remember from our files unit? What's the difference between those two types of storage? Right? And hard drive? Non-volatile, yeah. Or persistent and non-persistent. Right. So now from RAM, it loads that into the ALU's registers. Registers is just memory, right? So there's a little bit of memory built right into the ALU that says, okay, thanks for all that data. I'm going to start doing the math with it. But it doesn't necessarily know what to do with all this data yet. It has to get instructions from the CU, because remember, it's in control. So the CU tells the ALU, here's what you need to do with this data, right? And it's going to be simple. It's going to be some adding and stuff like that. But it kind of needs to know, like, what am I adding? And, you know, what do I do with the results kind of thing. So once the CU tells the ALU what to do, the ALU will do it. It'll do the math. Once it's done its math, it sends the answer, 2 plus 2 equals 4, back into RAM, which then eventually makes its way to our screen or a sound or whatever it was that it was actually processing, okay? But that's really the diagram that you guys can sort of visualize there, okay? And we can visualize it in the diagram I drew here as well, okay? So something outside of the CPU, which we know is really RAM and some sort of hard drive, or it could be the user, right? Maybe it's a keyboard. The user hit a key that then is coming in to the ALU. The ALU and the CU communicate with one another, and then results, once it's done the math, come back out. It's pretty simple, okay? It's a pretty simple system, okay? But it does get a little more obviously complicated than that. But let's just keep rolling, okay? So this is all just that silicon stuff. It's all just that switching going on there, okay? If you hear the word board, a board is just a piece of silicon that's being used in the hardware itself, okay? Those of you who have taken electronics probably have heard the term motherboard. Anyone heard that term? Motherboard is just the word they use to describe the main circuit board inside the computer. The term they use for boards that plug into it are called daughter boards. Get it? Mother, daughter, right? The daughter boards are things like sound cards, video cards. A card is just a board. The word card and board can be used interchangeably, okay? It's just really just all these switches again. Okay? But they all are just helping out that microprocessor. They're helping out the central processing unit. Okay. So, I mentioned this the other day. Back in the day, there was a difference between what was called CISC architecture and RISC architecture. Now maybe it'll have a little context to you. When they started developing hardware, they eventually went to more complex. So they said, you know what? Adding, that's too simple. Let's also make the computer do subtraction and multiplication and division and exponents. And instead of just and, or, and not, let's also give it way more complex stuff. Whereas the original computers used what's called the RISC architecture. which is a reduced instruction set. So in other words, just adding, right? That's reduced. Complex is let's give it more than just adding. And over time, they actually found that the RISC architecture actually worked better. If you keep the computer very simple, it works faster. And really, isn't that the way life is? The more complicated we make stuff, doesn't that tend to slow things down? Well, it's true in some ways. Okay, so where did the technology have to go? Well, the technology had to go into the programming. So the programmers had to get smarter. Because if we only have so many instructions, the actual programming languages had to get smarter. And they have evolved over time, right? You can actually program computers in ones and zeros, but it can move up from there to more complicated languages. Okay, so as I was saying, it didn't get used. Okay, so let's go a little deeper into the CPU, okay? Let's add a few more terms to it. In between as well, there's something called the IAS, okay? Immediate Access Store. This is memory, right? So it's another term that's essentially used. Again, you don't need to memorize all these acronyms, but that AIS is the essentially very much like the RAM, it's processing it there. So RAM is also called the IAS in some circles, okay? The buses, as we said, communicate, okay? Let's talk about the different buses. Data that moves in directions by the control unit is said to move on the control bus, okay? The address bus, addresses are memory, right? Memory has an address to it. So if it's an address bus, it's moving data to and from memory locations, okay? So the ALU does the math, the CU figures out the instructions, it passes data on control or address buses. It's all good. So now let's go back to our diagram for a second, okay? Now, what would you call this bus here going back and forth? What's it busing to and from? The control unit. So this would be a control bus, okay? Here it's moving to memory, right? So this stuff that I said was outside, which was just memory, now let's call it the IAS. Memory in terms of immediate access storage. So if it's going to and from memory, this is an address bus. Like it's passing it based on its address, okay? So you can kind of see how that works generally, okay? Okay. I think we're going to stop there for a sec for today. We'll pick this up a little bit more on Monday. But I just want to jump. I'm going to backtrack, not jump ahead. Pardon me. Backtrack to the very beginning where we started. Look at all this fun stuff. No, I want to go all the way. I should probably just do this. This would be easier. But oh well, there we go. I'm almost there now. This is what it says. So now let's take this in context. Outline the architecture of the CPU and the functions of the ALU and the CU and the registers within the CPU. Hopefully now that has more context to you. So let's see what it says. Students should be able to reproduce a diagram showing the relationship between the elements of the CPU, input, output, and storage, the memory address register, the memory data register are the only ones that need to be included. So here's two other acronyms that were not quite there yet. That's where I kind of had to stop today. But generally, you're ready now, I hope. This is kind of at least in your ballpark that you can do this, okay? Now, there's more stuff coming up down here that we haven't quite got to yet. But you have a general idea that this would be like a question. Like draw what the inside of a CPU essentially functions like. And you would draw something like this, okay? All right. I'm going to just stop there for today. We'll pick up a little bit more on this on Monday. And actually, okay, so let's pick up where we left off last week on this. And after your incredible performance just now. And let's take a look at just a few more advanced sort of terminology behind this. My apologies. No, maybe I'll leave them on. Okay, so the CPU, as you guys were seeing before, consists of the control unit and the arithmetic and logic unit, the ALU. Okay, those are the two main components. But it also through busing stuff around, we have memory as part of the CPU. Now we think of RAM as also memory, but memory is also built right into the CPU. And some other terms that come along with that. So there are two important memory registers within the CU called the current instruction register and the sequence control register, okay? Or the CIR and the SCR. I don't think the IB will require that level of detail, but let me just go into it a little bit, okay? So the current instruction register and the sequence control register. Now think about what those are. Imagine you're the CU. Imagine you're in charge of tons of information all day long. What do you think a current instruction register, knowing that the word register means memory, what do you think that does? It's remembering what? Yeah, it's remembering which instruction it's currently performing. So it's like a counter keeping track of which memory instruction I'm on. Because remember, you're going to then send it over to the ALU to actually do the math. So it's like, oh, I need to do math. Okay, ALU, take care of that math. So it remembers what the current instruction was that it was just executing. Okay? And then the sequence control register as well similarly keeps track of that sequence that's going on there. Okay? Inside the ALU, there's an important piece of memory called the accumulator, which is memory that accumulates as it like answers the question, what's like 2 plus 2, okay? So these memory registers are very important because they help you to sort of generate the memory needed to answer the questions that the CPU is constantly being asked. Okay, there's an additional register called the interrupt register, and it's exactly what it says it is. It will interrupt things if things come into the CPU that are important. So the CPU, and there's different things, the word interrupt in computing is used in different ways. Okay, so there's these different things that you'll often see that use the word interrupt with it. And it is what it says it is. It's interrupting actions, okay? Like when a computer crashes, that's an interrupt, right? Like it's interrupted the normal sort of game you were playing and it's put up something else that's important, right? Or if you're on, you know, you're typing an essay and you also have Skype running. Sometimes Skype will pop up. That's not quite an interrupt, but it's the right concept that something else is coming on there, okay? Another term you may be familiar with here is the word word, okay? A word is defined as a specific amount of memory, and the word is defined by different systems. So in different computer systems, a word is a certain amount. But generally, it's about 32 bits. 32 bits is what a computer would call a word's worth of memory, okay? Don't get confused. Don't think that that stores an actual word, like the word cat. It's not quite what it means, okay? And then buses we talked about. Okay. So in terms of buses, as we said before, there are two main buses, the address bus and the data bus. The address bus, its job is to specifically know where to place the data. And then the data bus is what actually brings the data along. So it's like two different buses working at the same time. And then there's a control bus in some systems, which is the one that's sort of like in charge. It's like a lead car leading them along the sort of path there. Again, I don't think the IB is going to need that level of detail in their questions, but you never quite know. We'll go back to the curriculum in a second to take a look at that. Okay? So if a microprocessor is described as operating at 500 megahertz, so obviously that's an older one, right? This means that 500 million instructions can be carried out by the microprocessor in 1 second, okay? A hertz is a unit of time, right? Okay, so megahertz, okay, is millions, right? So, okay. So this, though, I think is important. When we get down to the way the computer processes this, it uses something called the machine instruction cycle. Okay. At its simplest definition, it's called the fetch execute cycle. Okay? So let me just back up. I don't want you to read all that. Fetch execute. So you're the CPU. You fetch an instruction. You execute the instruction, right? So imagine on this table is a big pile of instructions, and I'm over here the CPU. So that would be like RAM, right? So over there in RAM is all the instructions I need to do. So I just go grab one and execute it, okay? But that's maybe a little too simple. So from there, we could also call it the fetch, execute, decode, okay? So what that means is I grab an instruction, I have to actually read it, go, oh, what does this mean? Oh, okay, now I know what it means, execute. So that's the decode process, is figuring out what the instruction actually means, okay? Then we could expand that even further to the fetch, execute, decode, store, okay? So the way I would describe that is, I'm the CPU, I grab an instruction, figure out what it means, oh, okay, I get it. 2 plus 2, I know what to do. Execute it, 4, I got the answer. I put the answer back here. So I store the answer. So that's what's called the machine instruction cycle. It's very simple, okay? But I want to kind of break it out in that sort of format to kind of give it an explanation for you guys, okay? Execute, decode, fetch, okay, etc., okay, and store. So when I decode, I'm getting an instruction from the CIR, fetching any data from the IAS. So those are acronyms we talked about a little bit, okay? IAS is immediate access store. That's essentially memory, right? You could say it's RAM, but it could also just be memory built into the CPU. The CIR, right? We remember that was a specific register within the control unit that got the current instruction. Oh, this is the instruction I'm getting, okay? Okay, so I've kind of put this into more of a flow chart for you guys, okay? So here's what the inside of the CPU is doing. This is like this is like the rule book for the CPU. Okay, I fetch the next instruction from my storage. I put it into the current instruction, right? So the current instruction is the one I just grabbed, okay? I decode that current instruction, and that might say, the instruction might say to me, add these 2 numbers. Oh, I need to go get those 2 numbers. So I go get the 2 numbers that I'm about to add. So I might need to go get more information to execute the instruction I've just been given. Then I execute it. So now I may give that to the ALU and say, okay, I need you to add these 2 numbers up for me. I now know what to do. Okay? Then I put the results back into storage over here. Okay? And then I'm a computer, so I just, okay, do I keep going? Is there anything else to do? And then I just keep going from there. Okay? So that's what's called the machine instruction cycle. It's similar to what we've been talking about with the whole diagram there, but it's just, again, that same sort of process that this is a machine, and the machine has to have a specific sequence here to do its job properly. Okay? All right, let's try to see if you guys got that, okay? With another little interactive thing. Wait.